All right, let's revisit some trends from our previous chapter. One of the trends we talked about was size. And if you remember from that previous chapter, when we think about size in the periodic table, here's a generic periodic table, and it goes down and to the left. When we think about ionization energy, here's our generic periodic table, and we go up and to the right. So size goes down and to the left, ionization energy goes up and to the right, and that's what we saw a while back in a previous video from a previous week. One thing that we can see now is electron configuration. And how does this help us better understand these ideas? Well, again, when we're looking at size, we're looking at things that are small. So things that are in the nanometer, picometer kind of range. 1/1,000th the size of a piece of hair would be an atom. And this is half of that atom, so to speak, if it's its radius. So if the radius increases as you move down a group, that just means that things get bigger. And it should make sense that as we get larger, it's because we have more protons, more neutrons, more electrons, and that's exactly what we see as we go down group 1 from hydrogen to lithium to sodium all the way down to francium eventually. So more rows to our stadium, we should be getting bigger. And that's exactly what we see with or without electron configuration. We can probably see that. As we go across, though, we actually get smaller, and that's a hard pill to swallow. Because you would imagine that if you're gaining protons, gaining neutrons, gaining electrons, you would be getting bigger. That's exactly what we just said. The disadvantage of moving across is your stadium cannot get larger. As you're moving across, you're just filling the same row of seats. So imagine, for an instance, that different from going vertical, if you're going down the periodic table, you're basically adding rows. However, if you're moving across the periodic table, you basically already have rows established. All you're really doing in that situation is adding more people to that row, or adding more electrons to that row. So we can't get any larger as we go across. That's the point. But what is unique about what's happening is all of these on the outside are electrons that are negative. Every time we move across one by one in the periodic table, we're adding more electrons, but we're also adding more protons down here in the center of the nucleus. And electrons and protons attract. So the more electrons we add, the more attraction they have towards the nucleus. And the more attraction they have to the nucleus, even though their stadium can't get any bigger, is going to make them shrink. So it is because of electron configuration that we can better understand why we shrink as we go across the periodic table. Eventually we get so small that we're gas-like, and that's where our noble gases will sit in group 18, and it's all because we have that attraction to the center when our stadium can't get any bigger because we're in the same row. Ionization energy, in my opinion, we probably don't really need electron configuration to understand that. What we said last week in lecture is that if you have 2 electrons and you lose 1, it's a big deal. So the energy for helium is through the roof because losing 1 of 2 is a big deal. That's losing 50% of what you have. Whether those are electrons or what we said with children, it's the same kind of issue. Radon, if you have 86 kids, it doesn't take a lot of energy to get rid of 1 of 86. That's a small percentage of what you have. We said if you take 86 kids to the mall, losing 1 of those kids, probably pretty easy because there's so many to watch after. And that's what we're after in that situation. So as we move across, we do get smaller. As we move up and down we get bigger. That's what we're after when it comes to size. When it comes to any of those concepts, just remember the overall direction, and you can compare one to the other pretty quickly. Another thing that we're looking for to understand in this chapter based on electron configuration is how we become ions in the first place. Again, the goal of a lot of elements is to be noble gas-like. What does that mean? Well, some can lose, some can gain electrons to be at least similar to noble gases. There is no possible way to be a noble gas because you can't change your protons, you can't change your neutrons. But you can feel like a king or a queen by gaining or losing electrons, and that's exactly what happens in the periodic table. Definition-wise, what's most common in introchem is that metals will lose electrons. Remember, electrons are negative. If you're losing your negative, all of your positive protons are still with your metal. So if your positive is still there, but you're losing your negative, your positive remains. And that's why we get to a positive ion. Nonmetals, they have protons too. But if you're gaining electrons, electrons are negative, and if you're gaining more negative, you're going to become negative as a result. So be careful with those definitions because it's easy to get them backwards. A lot of students associate losing electrons like losing weight, and that's a negative relationship on your body. But in chemistry, all that positiveness is still inside of your body, inside of your nucleus, so it's still there, so you're positive in the end. So it's opposite of your gut feeling. So be aware of that and be careful about it. Mostly what elements tend to follow, and this is what we saw with the rule of 8, this law of octaves that we saw in a previous lecture. This octet rule is the easiest way to recognize the magic number needed in order to lose or gain electrons to fill or empty a electron configuration. So you can imagine with sodium and chlorine, what's happening here is you have an electron on the outside, and then you give it to an element that needs an electron on the outside. So underneath, sodium's going to have 10 electrons, like a noble gas. And then because we fill chlorine over here, we're going to be now full with our 18 electrons in the end. So here we have a neon configuration. Here we have a argon configuration. And both are perfectly happy. It has noble gases in the end. Because it took one sodium, that was a positive one sodium. It took one chlorine, negative one chloride. These would just squish together and make sodium chloride. Let's think about that in a little bit more detail with electron configuration. So let's pretend that sodium's a metal, and it is. It's an alkali metal. On the periodic table, we would go 1s2, 2s2, 2p6, and then 3s1. For chlorine, we would go the same distance, but a little bit further. 1s2, 2s2, 2p6, 3s2, and then 3p5. If we were to look at the noble gas configuration, we would find the last p6, because usually things are bigger than helium at 1s2. So here's helium, here's neon. So let's take neon and write Ne3s1. Here again is helium, here again is neon. So let's take neon and see that there's 3s2, 3p5 left. What's unique about these is we can get rid of 1 or gain 7 with sodium, or with chlorine we can get rid of 7 or gain 1 with chlorine. There's always an easier choice. There's two choices always, but one's always easier. And what we're going to see very quickly is if we take this electron and give it to chlorine, that would take sodium to sodium plus 1. It would now feel exactly like neon, the noble gas. But now by filling this, we are now like argon, because now we're 3p6, and that's like chloride, the -1 ion. Both noble gas-like, check. Together they attract each other because positive and negative attract, and we get NaCl, the compound. And that's chemistry. That's most of this textbook, just in various different ways do we show it. We see the same thing here for magnesium. What's different about magnesium, though, in this circumstance is magnesium has 2 electrons to give because it's in Roman numeral 2. It's an alkaline earth metal. But all halogens, like chlorine that we saw before, and now fluorine that's on this slide, these guys have magic number 7. And 7 can't take 2 electrons. It can only take 1 to make the magic number 8, the octet. So only 1 electron goes here, the other electron goes there, and now magnesium with 2 fluorine ions, called fluoride, is going to give you MgF twice, because it took 2 fluorines to satisfy the giving of 2 electrons from magnesium. Fluoride couldn't accept 2, so it took 2, accepting 1 each, to deal with the 2 electrons that magnesium wanted to give up. And this is what we see and what we've seen before on the periodic table. So let's show you that one more time. If we have the periodic table in its generic sense, we have our first 2 families of the periodic table. This is family 1 and family 2. These guys are going to go backwards. They're going to be a +1 because they're going to lose their S1 electrons. These guys are going to go back 2. That's going to be a +2. We just saw with the entire transition metals that they have S electrons that precede their D electrons and energy level. So over here was a 4s2 and then a 3d, whatever. For iron it was a, 5 or 6n. So all of these is a +2 and others, which is why it gets tougher in the next chapter when it comes to naming and so forth. We'll see that in week 5. As we get over here to the P section, we have 5 of these plus the noble gases. We have that bold stair-step line that determines metals from nonmetals. Remember, these guys are already happy they have no charge. But if these guys are going to move forwards, noble gases are going to be -1. These guys are going to be -2 because they're going to move 2 families over to be like noble gases, -3, -4. Just like underneath, you're going to see going back this one plus these 2, because we're skipping over the transition metals. These are going to be +3 and then +4. And that's really all we deal with in Introchem. You could imagine it continues though. When it comes to Roman numerals, this would be Roman numeral 3. This is Roman numeral 4. Notice it's for negative and positive. It's just different across the metalloid line. And then we have 5, 6, 7, and then 8. There's the magic number. So it's all about how do we get to that magic number. Is it by losing electrons? Because that's what metals do. They go backwards, they go to the left. If you're losing electrons, you're going to become positive. But if you're up here in this upper kind of category here, you're going to be going to the right. That's gaining electrons. And that's going to make it negative. So electrons are negative, you're gaining negative, so you become negative. And that's a summary of how to think about these ideas just by glancing at the periodic table. So what I would do when I see a periodic table is I would use that information and then label it. So this tells me that this entire family is +1, +2. As long as I'm underneath, this is +3, +4. Above is going to be -4, -3, -2, -1, and then obviously these guys are 0. So just by realizing that dark metalloid line, we're putting a lot of those chapters together to better understand what's possible. So all of these over here, these guys are losers. They're going to become positive. All of these over here, they're going to become gainers. And those are going to become negative. That's the summary of almost 2 chapters in a row. This is what we're building towards in order to use throughout the semester. So we should be able to look at any of these examples and start to make compounds just like we did a little bit at the end of our week 2 material. So for some of these we would find, say, sodium. Sodium is in group 1, so that's a +1. It's going to lose its S1 electron. So this is again a Roman numeral 1 kind of atom. Oxygen, it's in family 6. It's a chalcogen. It's going to be a -2 because it already has 6. It needs to go to 8. The only way to get there is to gain 2 electrons. Sodium has 1, it gets rid of 1 to get back to 8 on the previous noble gas. And that's why it became +1. It still has its 11 protons, but now it only has 10 electrons because it gave this electron, or in this case, several, will give electrons to oxygen. So if you have a +1 and a -2, we said cross charges. So take a 2, cross it over, take a 1, cross it over. We get Na twice, oxygen once. You can put that imaginary 1 there if it makes you feel better. It's kind of redundant to have it there. This just tells us that 2 positive 1s is equal and opposite to 1 -2. So as long as those balance, our compound is correct, so Na2O. And again, this is by using the crossover rule. So the crossover rule works great. Just remember that if you always use the crossover rule and the charges are the same, you're going to have to reduce those charges when possible. So here's a couple more. So let's try a couple of these out. So lithium, group 1. So lithium is +1. Nitrogen, group 15, that's a -3. It's got 3 families to go, basically, to be a noble gas. Cross the 3, cross the 1. So you get lithium 3 times, nitrogen once. Magnesium, group 2, is a +2. Oxygen is group 16, that's a -2. It's got 6, it needs 8. Magnesium had 2 extras, so that was a perfect match. So we can just squish those together into MgO. Here we have 2 nonmetals, so it's a little bit trickier, but remember hydrogen does sit in the alkali metal family at least, so it will share the same kind of common charge of +1, it's in group 1. Oxygen, again, a -2, so in this situation we can see why it's H2O when we cross charges. Aluminum is in group 13, so that's a +3. Sulfur is in group 16, that's a -2, just like oxygen, same family, same charge. Cross the 2, cross the 3. So aluminum twice, that's going to be a +6. Sulfur 3 times, that's a -6 that balances. Carbon is in group 14. It's Roman numeral 4, so we can lose 4 or gain 4. We're going to say lose 4 in this situation because we have oxygen that can gain 2. Cross 2, cross 4. We temporarily get C2O4. Just remember that you can reduce those and get CO2. So reduce the 2 by 2, reduce the 4 by 2. Take that common multiple out, and you'll get that answer of CO2, carbon dioxide. KBr, we have group 1 +1. Potassium, we have a halogen. Group 17, that's a Roman numeral 7, so it's gaining 1 electron. Potassium happens to want to lose 1. So again, that's a perfect match. So that's just KBr. And that's what we're looking for in this situation. The rest of this chapter is just reminding you that this is intro chem after all, even though some lectures it may not seem like it, may seem like we're going a little too far. What's important to realize is that there is more to the story. We're just stopping here for intro chem purposes. So Schrodinger came along after Bohr and decided and discovered that it's not really possible to know where an electron is or where it's going. This uncertainty principle shows us that our understanding of an atom has got a long ways to go. When we say orbit, now we're going to say orbital. An orbital is a 3-dimensional shape that defines the position of where an electron should be 95% of the time. But that doesn't mean that we know where the other electrons are during that given amount of time. Obviously, these are way too small. This is, millions of times smaller than a piece of hair, billions of times smaller when you come to electrons probably. So there's no way to possibly know where they're at as they are moving, in and about the atom. But we do know that they prefer to be in a certain position, and that's what we've been describing with electron configuration. So really when we say the s sublevel, really what we mean is the s orbital. That just means this is the defined cage, the defined shape, the defined chair, section or sublevel, doesn't matter how we call it. It's basically where to find those s electrons 95% of the time if we were to want to find one and not care about the others. p orbitals are more like dumbbells, and then d orbitals are more like little flowers, which are double dumbbells. For purposes of the homework, what's most important to realize is that s and sphere go together, and that helps us. Obviously p and dumbbell do not, so be careful there. D's we don't really deal with too much in intro chem, just because again they are in that kind of balcony rule breaking kind of category. So as we come full circle to the beginning of our first video to our end of our last video, just remember that it is complicated. This idea of orbits with Bohr and now orbitals with Schrodinger really describe the process of being excited and then going back to our ground state. So as an example, what we need to realize is that if lithium were zapped by electricity, its electron jumps from an s to a p. What that really means, though, is that the orbital that is now a sphere, and it's, so here's our spherical shape, which is our s. If it were to jump to a higher location, it could be a p, and that means that now it's going to switch to this dumbbell shape. We can't see that. We can't see the jump in energy. We can't see it excite. But when it returns to its ground state, it's going to produce a photon. And that photon has a specific color based on the distance of where it was and how far it jumped and how far it fell. So that can happen in multiple steps or in one step, and that determines the color, the energy of the photon specifically. So the short story is orbitals can change shape. And when they change shapes, they can change back and produce photons of color. So as you look at your homework, realize that everything that we've done in this class has been ground state configurations. Ground state configurations look perfectly normal to the periodic table. So again, we would call these normal. If you're looking for excited states, look for things to be weird. So look in this situation, notice we have a 1. That should be a 2. It's because this 2 electron jumps out to a p orbital. So it jumped from a sphere to a dumbbell. So that jumping, that weirdness, that's what we call the excited. And then lastly, something that's probably the easiest to recognize is a overfilling. You can only fit 2 in an S, not a 3. So 3 is impossible because there's not 3 boxes in the S section of any periodic table ever. So look for numbers higher than 2 in an S, higher than 6 in a P, higher than 10 in a D, and you'll find those answers pretty quickly. So be careful with these. Usually this one here, this excited state one, is usually the issue because a lot of students glance over the middle, and that's usually where the electron is missing that has been excited. And that finishes our week 3 and the material for exam 1. Happy studying.